Hey everyone, and welcome! Today we're going to break down one of the trickiest question types you'll find in chemistry, the assertion-reason question. In this explainer, we'll use core chemical reactions to build a simple, powerful strategy you can use to nail these questions every single time. Okay, let's just jump right in with a puzzle. Take a look at this. The first part, the assertion, seems pretty straightforward, right? But what about the reason? And here's the real kicker. Does that reason actually explain the assertion? See, these questions aren't just about what you know, they're about understanding why things happen. So let's build the toolkit to solve this and any other question like. So, here's our game plan for today. We're going to start with a foolproof method for any assertion-reason question. Then we'll dive into the chemistry itself, balancing equations, spotting different reaction types, and getting a handle on energy and electrons. We'll even see how this stuff shows up in your daily life before we wrap it all up with a solid strategy for you to take away. All right, first things first, let's face our enemy head-on. The assertion-reason format can look a little scary, but it's really just a logic puzzle. And the good news is, there's a simple plan of attack that works every single time. This right here is your secret weapon, the AR drill. It's a super simple three-step process. Step 1, just look at the assertion. Is it true? It's a simple yes or no. Step 2, now completely ignore the assertion for a second and just read the reason. On its own, is it true? Another yes or no. And finally, step 3, and this is the most important part. If they're both true, you have to ask yourself, is the reason the correct scientific explanation for the assertion? And that right there is where almost everyone gets tripped up. But not you, not after today. Okay, let's get into our first big concept. You know how you're always told to balance chemical equations? Well, it's not just some random rule your teacher made up. It's about following one of the most fundamental laws of the entire universe. And this is that law, the law of conservation of mass. It's basically chemistry's #1 rule. You can't just create or destroy atoms in a chemical reaction. You can only rearrange them into new combinations. So whatever you start with, you have to end with, just in a different form. This is the why behind all that balancing. So how do we actually do this? Let's walk through it together with this reaction of iron and steam. First, we just make a quick list of our atoms. A good strategy is to start with the most complicated-looking thing, which here is that Fe3O4. To get our 4 oxygens on the right, we have to put a big 4 in front of the H2O on the left. But wait, now that messes up our hydrogen count, right? We have 8 on the left now. No problem. We'll just put a 4 in front of the H2 on the right to match it. Last step, we need 3 irons on the left to match the right. And boom, we do a final check and it's perfectly balanced. See? Just a step-by-step process. All right, let's apply our new AR drill. Step 1, is the assertion true? The equation must be balanced. Yes, of course it must. That's a true statement. Step 2, is the reason true? The law of conservation of mass says atoms must be equal. Yes, that's the definition of the law. That's true. So now the final step, does the reason explain the assertion? Absolutely. The law of conservation of mass is the exact reason why we have to balance equations in the first place. So this is a perfect pair. All right, we've got the master rule down. Now let's fill up our chemical toolkit by learning to spot the 4 main patterns that chemical reactions follow. If you can recognize these patterns, you can pretty much predict what's going to happen. First up, we've got combination reactions. Just think of it like this. A plus B comes together to make AB. A couple of simple things combine to make one more complex thing. A really cool example is when you add water to quicklime. It gets super hot, sizzles, and the two combine to form a single new substance, slaked lime. And next, we have the total opposite, decomposition. This is where one big thing, AB, breaks down into its simpler parts, A and B. And you usually have to give it a little push, you know? You gotta add some energy, like heat, to get those bonds to snap. Like here. Heating up limestone forces it to break apart into quicklime and carbon dioxide gas. It's absorbing heat, so we'd call this an endothermic reaction. Okay, check this out. This is a perfect picture of a displacement reaction. It's exactly what it sounds like. A more reactive element literally kicks out or displaces a less reactive one from its home. In this beaker, the iron in the nail is more reactive than the copper in that blue solution. So the iron jumps into the solution, kicking the copper out. And you can actually see it happening. That brownish stuff forming on the nail, that's the copper. And the blue solution gets lighter because the copper sulfate is being used up. All right, you might want to screenshot this one. This is your ultimate cheat sheet for telling these reactions apart. If you end up with just one product, it's combination. If you start with just one reactant, it's decomposition. If you have an element and a compound swapping places, it's displacement. And if you have two compounds that just swap partners, that's double displacement. Simple as that. Let's run the drill again. Assertion. The nail becomes brownish. Is that true? Yep, we literally just saw the picture. That is true. Reason. Iron is more reactive than copper and displaces it. Is that true? Yes, if you look at a reactivity series, iron is above copper. So the reason is true. Final question. Does the reason explain the assertion? It sure does. The fact that iron is more reactive is precisely why it kicks the copper out. And that copper is what forms the brownish coating. Another perfect match. Okay, so we can spot the what. We know what kind of reaction it is. But now let's dig into the why, the invisible forces that are actually driving all these changes. We're talking about the flow of energy and the trading of electrons. So, every reaction either releases energy or absorbs it. If it releases energy and makes its surroundings feel warmer, we call it exothermic. Think about a campfire or even your own body. The reason you're warm right now is because of respiration. Your body is running a slow, controlled exothermic reaction to get energy from your food. The opposite is endothermic, where a reaction sucks in heat and makes things feel colder, like many of those decomposition reactions we talked about. Now for a really crucial concept, redox. It's just a mashup of two words, reduction and oxidation. Let's keep it simple for now. Oxidation is when something gains oxygen. Reduction is when something loses oxygen. And here's the key. They are partners in crime. You can't have one without the other. If one thing is losing oxygen, something else has to be there to gain it. And look at that. This brings us right back to that very first puzzle we started with. When you see that magnesium ribbon burning with that incredibly bright white flame, what's happening? It's grabbing oxygen from the air. The magnesium atom gains oxygen. So what do we call that? We say the magnesium has been oxidized. This picture is the perfect definition of oxidation in action. Okay, let's put our redox knowledge to the test. Assertion. Is the copper oxide being reduced? Well, let's see. It starts as CuO and it ends as just Cu. It lost its oxygen. And what's the definition of reduction? Loss of oxygen. So yes, the assertion is true. Now for the reason. Does it lose its oxygen to the hydrogen? Let's check. The hydrogen starts as H2 and ends as H2O. It gained the oxygen. So yes, the reason is also true. Final step. Does the reason explain the assertion? Yes, the reason it's called reduction is because it loses oxygen. It's a perfect explanation. So, I know we've been deep in the chemistry weeds, but I promise this stuff isn't just for exams or a lab. These exact reactions are happening all around you, every single day. That bright, fast oxidation of magnesium is cool, but oxidation can be slow too. You know that rust on an old car? That's just oxidation happening in super slow motion. And have you ever smelled old cooking oil or butter that's gone bad? That funky smell is also oxidation, a process called rancidity. And here's a cool little tip. You know why your bag of chips is so puffy? To stop the fats in the chips from oxidizing and going stale, they flush the bag with nitrogen gas to push all the oxygen out. Phew! We have covered a ton of ground, so let's take a breath and bring everything back together. Let's lock in your personal strategy for success with these assertion-reason questions. Here it is, your simple 4-step plan. First, just figure out what the question is really about. Is it balancing? Is it redox? Once you know the topic, run the drill. Step 2, check the assertion. Is it true? Step 3, check the reason. Is it true? And step 4, the final boss, check the link. So let's go back to our very first question. Assertion, magnesium burns to form a white powder. True. Reason, magnesium is reduced. Wait a minute, we just saw it gains oxygen, which means it's oxidized. So the reason is false. And if the reason is false, we don't even have to worry about step 4. Problem solved. And that brings us to the end. I want to leave you with one final thought. Here's the real secret to mastering these things. Start making your own. Seriously. Take any statement from your textbook, like respiration is an exothermic process. Make that your assertion. Then try to write a correct reason for it. Then try to write a reason that's true but doesn't explain it. The moment you start thinking like the person who writes the test, you'll find these questions aren't so scary after all. You've got this.